Commercial drone delivery offers a specific logistical proposition: rapid last-mile transit times, reduced road traffic, and lower operational emissions. Deploying these fleets across metropolitan airspace also introduces immediate environmental externalities. The two most prominent are the physical intrusion of localized acoustic noise and the spatial disparity in who actually receives the delivery service versus who is subjected to the sound. These externalities carry an immediate civic consequence. As exposure accumulates, communities react with severe resistance, driving an influx of formal noise complaints to local representatives. Existing logistics literature and municipal planning models generally treat carrier operations as static variables. They map a route, assign a vehicle, and assume the operational behavior remains fixed regardless of the civic environment. That assumption fails in practice. Private logistics carriers and local consumers are highly reactive. The moment a municipal planner tightens a flight cap or relaxes a curfew, carriers shift their dispatch priorities and consumers change their ordering habits to match. Attempting to forecast these outcomes with static models is ineffective. Urban logistics operates as an endogenously coupled socio-technical system, requiring a methodology that accounts for constant behavioral adaptation. To address this gap, researchers developed a complexity-aware, agent-based policy sandbox. It is designed to test how interacting municipal rules influence delivery systems under conditions of uncertainty. Rather than attempting to predict exact delivery volumes for a specific city, the sandbox acts as a controlled environment to map the continuous feedback loop between local regulations, corporate operations, and resident reactions. The study isolates a specific governance mechanism, evaluating whether complaint-responsive flight cap rules can actually stabilize regulations over time without suppressing overall delivery adoption. To answer that, the simulation derives the entire urban loop from first principles, tracking an individual consumer's choice all the way up to a municipal regulator's zone-wide policy decision. This diagram maps the macro architecture of the simulation, linking cause and effect across 6 interconnected stages. The cycle begins here at the policy regime node. This establishes strict operational constraints for the delivery fleet, defining flight volume caps and minimum altitude floors. The simulation deploys these rules across a parameterized metropolitan geography, divided into 4 concentric municipal zones radiating outward from a central fulfillment depot. Within these zones, the model populates a demographic layer consisting of 200 heterogeneous resident agents. Each resident agent possesses unique baseline variables. They are individually assigned a localized ambient noise level based on their specific coordinate, as well as an inherent, randomized sensitivity to privacy loss. By structuring the population with diverse variables, a single uniform policy change triggers radically different responses depending on which zone a resident occupies and their individual sensitivity threshold. The loop advances into the Drone adoption and road van substitution nodes. Here, a multinomial Logit model evaluates every order, assigning a fulfillment mode by weighing delivery cost, time urgency, and the resident's privacy sensitivity. Drone dispatch requires strict operational clearance. The parcel must weigh under 2.5 kilograms, it must fall within battery range, and the zone must have capacity. If a consumer selects drone delivery, but their specific zone's flight cap is already saturated for the hour, the system engages a substitution mechanism and reassigns the order. The overflow volume is redirected to the fallback mode, standard road van fulfillment. Enacting strict drone regulations does not eliminate consumer demand for rapid delivery. It redirects that demand into ground-based networks, carrying secondary impacts for surface road traffic. Advancing to the physical acoustic exposure node, the simulation calculates the 3D slant distance from a drone's trajectory to residents below. Elevating the regulatory altitude floor from 50 to 80 meters physically reduces the event sound level by 2.07 decibels.
But physical sound pressure doesn't equal civic action. The simulation filters this raw acoustic data through the community complaints node. Annoyance is cumulative, but countered with an asymmetric memory decay function as residents gradually acclimate to older acoustic events. The decay curve spikes violently only when an acoustic event registers high enough to exceed both the local ambient background noise and the municipal regulatory threshold simultaneously. Even with high annoyance, logging an actual complaint remains a probabilistic event. The likelihood of a resident picking up the phone relies heavily on their localized privacy sensitivity and whether they have a documented history of filing complaints recently. Acoustic propagation equations map the physical footprint of a drone fleet, but regulatory impact is dictated by the complex psychological accumulation and eventual decay of community annoyance. The cycle concludes at the adaptive governance node. At the end of a 15-day operational epoch, the municipal regulator calculates the cumulative complaint rate for each of the 4 zones. This time series graph evaluates a traditional binary controller. If a zone records a complaint rate above 34 per 100 residents, the municipality tightens the flight cap. If the rate sits at 34 or below, they relax the cap. The study compares this against a 3-state controller. Regulators tighten above 38 complaints and relax below 30. Between those markers lies a deliberate maintain deadband. To see the impact, we isolate a specific simulation run, SEED 402. Zone 1 concludes Epoch 1 with a highly elevated complaint rate of 50. The regulator responds by reducing the flight cap from 20 down to 16 flights per hour. Following the reduction, Zone 1 registers exactly 32 complaints in Epoch 2, landing squarely inside the shaded maintain zone. Under a binary rule, registering a 32 would mandate immediate relaxation of the flight cap, instantly reversing the previous decision and beginning a persistent seesaw effect. But under the 3-state controller, the algorithm simply absorbs the fluctuation. The municipal flight cap remains completely frozen at 16. A maintain state filters out minor statistical variations in civic annoyance. Regulators intervene when necessary, but ignore the ambient noise of a functioning system. Scaling up from a single run, the researchers executed 960 matched policy seed cases to evaluate the aggregate trade-offs of these governance structures. This chart compares total regulatory movement. The 3-state controller reduced cap volatility by 15.66 units per run compared to the binary controller. Implementing the maintain deadband achieved this massive drop in volatility with 0 detectable penalty to transit equity and virtually identical complaint rates. Examining the specific policy levers, this scatter plot tracks the trade-off between drone adoption and community complaints. The optimal outcomes cluster in the lower right. Policy packages combining an 80-meter altitude floor with permissive noise thresholds generate the fewest complaints while preserving high adoption. Elevating the altitude physically mitigates the acoustic exposure, while adjusting the regulatory threshold modifies the behavioral trigger point for civic action. Managing a drone network requires utilizing both levers. The operational directive for municipal planners and aviation authorities is clear. When writing adaptive regulations for urban air mobility, the inclusion of a maintain band is necessary to prevent perpetual policy oscillation. The exact complaint frequencies output by this specific ABM are simulated indicators testing a structural thesis, not empirical forecasts guaranteed for a specific municipality. Human reporting behavior resists perfect static forecasting. City planners cannot predict exactly how many residents will call to complain on a given Tuesday. Instead, they must optimize the regulatory structure itself for resilience. Urban drone delivery operates in a continuous, complex feedback loop. To successfully scale it, the policies governing the airspace must be as responsive and adaptable as the populations living directly beneath it.